Well, we've just finished covering our discussion of gases and the gas laws, so the logical place to go now would be to talk about liquids. Chapter 14 discusses the various properties of liquids. Way back at the beginning of the semester, I asked you guys a question, and that is, why are some things solid, like this copper wire, some things are liquid, like water, and others are gases, like hydrogen? It turned out that the difference, what determined whether something was a solid or a liquid or gas, was the strength of the attractions between the particles. Turns out that hydrogen molecules have very weak attractions, which is why they simply float apart and form a gas. Water molecules have a moderate or intermediate attraction. The attractions are strong enough to keep the water molecules from simply floating away, but they're weak enough that allows the water to move around. Something like copper has very strong attractions, so the copper wire maintains its shape. The atoms of copper are very strongly attracted to one another. Back when we talked about this at the beginning of the semester, you guys didn't have enough knowledge of chemistry for me to really explain why. Why are the attractions weaker in water than they are in copper? Why are the attractions in water stronger than they are in hydrogen? At that point, you just didn't have enough background. Now we're near the end of the semester, and you have hopefully learned a lot. So in chapter 14, we're going to talk about the nature of these so-called intermolecular forces, these attractions that bond substances together. A lot of it is going to be based on the shapes of the various molecules. So we're going to spend time going back to what we learned in chapter 12 about 6 weeks ago, where we described the shapes of various molecules. It turns out that the shape of a molecule has everything to do with how strong its attractions are and whether a substance is a solid or a liquid or a gas. So, lots to cover in this chapter. Why don't we go ahead and get started? Now, all of the properties that liquids have depend on one thing, and that is something called intermolecular forces. Basically, these are just the forces of attraction that exist between molecules. Without intermolecular forces, there would be no such thing as liquid water. These forces hold the molecules of water together. Without these forces, DNA could not exist as a double helix. The molecule would simply unravel. In fact, without intermolecular forces, life as we know it could not exist. So what is the nature of these intermolecular forces? Well, first, let's consider ionic compounds. What is it that holds the ions together in ionic compounds? Why do ions stick together? It's simply because they have opposite charges. For example, in salt, a sodium ion is attracted to a chloride ion because they have opposite charges. This is a representation of a crystal of sodium chloride. The purple represents the sodium ions, the green represent the chloride ions, and all of these ions simply stick together because the opposite charges attract one another. Now, do molecules stick together? Well, of course they have to. Because if they didn't stick together, for example, as we mentioned earlier, water could not exist as a liquid. The only reason liquid water exists is that all those water molecules are attracting one another. Sugar could not exist as a solid if the molecules of sugar were not attracted to each other. So without those intermolecular forces, there would actually be no liquids or solids. Everything would be a gas. But why do molecules stick together? Well, it's the same reason that ions stick together, because opposites attract. It's pretty obvious why ions attract one another. When two atoms come together and form an ionic compound, one atom ends up positive and the other negative, and so obviously the two are going to attract one another. But what about molecules? How can molecules have positive and negative charges? When two nonmetals come together and form a covalent bond, they're sharing electrons. One atom is not taking the electrons from the other, and so they're not forming a positive and negative ion. So what is it that allows molecules to have positive and negative charges? The answer is a property known as electronegativity. Whenever two atoms form a covalent bond, they both actually want electrons. They would both love to take those electrons, but they can't because the other atom is unwilling to give them up. So they have to share, but it doesn't mean they're going to share equally. Electronegativity is basically a measure of how strongly atoms attract electrons. So whenever there's a covalent bond between two atoms, both of those atoms are pulling on the electrons. We can gauge the electronegativity of elements by simply looking at their location on the periodic table. As you go down the table, electronegativity decreases. Therefore, of course, as you go up, it increases. As you go across the periodic table, electronegativity increases. So the most electronegative element on the periodic table turns out to be fluorine. It's the farthest to the right and the farthest to the top if we ignore the noble gases. And of course, we do ignore the noble gases because they don't want electrons at all. They have no interest in getting electrons. And of course, the least electronegative element would be in the opposite corner. Francium is the farthest to the left and the farthest to the bottom, making it the least electronegative element. Now let's take a look at some molecules. The hydrogen molecule consists of two atoms of hydrogen. Each one contributes one electron to form a covalent bond. So initially, each hydrogen atom owns one electron. When they form the covalent bond, they each contribute one electron to that bond, and so essentially they now own half of a pair of electrons. Well, from an electron standpoint, whether you are the sole owner of one electron or the half owner of a pair of electrons, it comes out mathematically to be the same. And so the hydrogen molecule is neutral. It has no positive or negative charges. The hydrogen went from one proton and one electron to start with, and it has one proton and half a pair, or one electron, to end with. The same is true with the fluorine molecule. Each fluorine contributed one electron to a bond, so the fluorine atoms went from being the sole owner of one of those electrons to the half owner of a pair of electrons. And so the fluorine molecule, like the hydrogen molecule, is balanced and it's neutral. Now what happens when two atoms are not the same? The fluorine atom is, of course, much more electronegative than hydrogen because fluorine is the most electronegative element on the periodic table. So hydrogen and fluorine don't share equally. The fluorine is pulling the electrons toward it, so the fluorine is getting the lion's share of the electrons. Perhaps the fluorine now has 2/3 of the pair and hydrogen has only 1/3. That means that hydrogen is missing a bit of electron, and therefore that gives the hydrogen a partial positive charge. And the fluorine, because it's getting the lion's share of electrons, has a partial negative charge. This Greek letter delta represents partial. So anytime you see delta plus or delta minus, that simply means that it's a fraction of a charge. Now, as an analogy, let's consider the sun and a cloud. So we'll imagine that the sun represents the proton in the nucleus of the hydrogen atom, and the cloud is that electron. In a hydrogen atom by itself, that electron is completely covering the proton, and so you don't feel the positive charge because it's being blocked by the electrons, just like we don't feel the sunlight because it's being blocked by the cloud. Now, suppose the cloud begins to move away from the sun. It slowly begins to expose part of the sun. So now we don't feel the entire intensity of the sun, but we just feel part of it. Sort of the same kind of thing that happens with our hydrogen fluoride molecule. As the cloud of electrons is pulled off of the hydrogen atom, that positive nucleus, or that proton, begins to peek through, and we begin to feel part of its positive charge. Because the hydrogen fluoride molecule has a positive and negative charge, we say that it has what's called a permanent dipole. Dipole simply means two poles. So just like a battery has a positive and a negative pole, the hydrogen fluoride molecule also has a positive and negative pole, and permanent simply means that it's always present. We can also refer to hydrogen fluoride as a polar molecule. A polar molecule is simply a molecule which has poles. So a hydrogen fluoride has a positive and negative pole. It is a polar molecule. And then finally, the reason, of course, that hydrogen fluoride molecules attract one another is because of these poles. The negative fluorine end of one molecule is attracted to the positive hydrogen end of another molecule, and so all of these hydrogen fluoride molecules can link together. And that's the nature of the intermolecular forces in these polar covalent molecules. Now, what about molecules that only contain one element? Molecules like that, of course, are going to have to share equally. For example, in the hydrogen molecule, as we've said previously, because the two hydrogen atoms have the same electronegativity, the cloud of electrons will remain equally distributed around the molecule, and the hydrogen molecules have no charges. There is no positive or negative pole. So we refer to molecules like this as nonpolar molecules because they don't have a positive or a negative pole. So here's a fact for you. All intermolecular forces are due to positive and negative charges in molecules. So the only way that two molecules can attract each other is they have to have a positive and negative pole. So here's a question for you. Do nonpolar molecules attract each other? Well, we've just said that the only way molecules can attract each other is to have positive and negative charges. And we've already said that nonpolar molecules don't have those. So will they attract each other? And the answer is absolutely. And you're thinking, now wait a minute, that seems like you just contradicted yourself. But the fact is, it's pretty obvious that nonpolar molecules must attract each other. For example, if you look on the periodic table, most of the elements on the table are solids, yet each individual element consists of only one kind of atom, which means they're not polar, yet somehow they're sticking together. If you take something like nitrogen, which is a gas, you've probably heard of liquid nitrogen before. They use it to take warts off and such. They use it to cool magnets. And the only way to get liquid nitrogen is you lower the temperature until the molecules stick together and form a liquid. If nitrogen molecules, which are nonpolar, didn't attract each other, it would be impossible to turn it into a liquid. But the fact is, all substances, if you lower their temperature far enough, they will form liquids. And that proves beyond all doubt that those substances must somehow have attractions for one another. So let's see if we can figure out how we can address this apparent dichotomy here. How can molecules that apparently don't have poles attract each other when the rule is they have to have poles to attract each other? As an analogy, let's take a look at the Indianapolis Motor Speedway. That's where they run the Indy 500 road race. It's a 2.5-mile track, and the track is perfectly symmetrical. So each half of the track is exactly the same as the other half of the track. So logically, how much of the race would a particular car spend on the right side of the track compared to the left side? Well, since the track is symmetrical, we would expect it would take the car just the same amount of time to go around the right side as it did the left, and each individual car should spend half their time on each side of the track. Sort of like the electrons in a hydrogen molecule. They spend half their time on one side of the molecule and half on the other, which is why it's balanced. However, if you looked at the track from the air, suppose we went up in the Goodyear blimp and we took a photograph of the track at some point in the race, would you expect to see half the cars on one side and half the cars on the other? Very unlikely. More likely, you would see probably a bunch of cars, piled up on one side of the track and a few stragglers or the leaders on the other side. If you took another picture a few minutes later, you might find the opposite. Now there's a bunch of cars on the right and not very many on the left. If you took 1,000 pictures during the course of the race, and in each picture you counted the cars on the left and on the right, and you added them all together, you'd find that it came out equal, that the cars spent half their time on one side and half on the other. But for any instant in time, if you froze the action in a particular instant, you would find that it's not balanced, that there's more cars on one side than the other. The same thing can happen in molecules. Normally, we would expect in a hydrogen molecule to find the electrons equally distributed around the molecule. So half of them are on the right and half are on the left. But because the electrons are sort of randomly flying around in the molecule, it's possible that for a moment we might find the electrons on one side of the molecule rather than the other. Now, for this particular instant in time, the electrons have moved to one side, and now this end of the molecule has more electrons, and it makes this end of the molecule negatively charged, and the other is positively charged. So, nonpolar molecules have what's known as a temporary dipole. Most of the time, the hydrogen molecule is nonpolar because the electrons are equally distributed. But at some time, we'll find the electrons are off balance here. The electrons have moved more to the one side than the other, and for that moment or that instant, the molecule will be polar, but it'll only be polar temporarily. So nonpolar molecules only have positive and negative charges some of the time rather than all of the time. So in general, a molecule with a temporary dipole will not have as strong of intermolecular forces as a molecule with a permanent dipole. So what determines the strength of the intermolecular forces in a molecule? It depends on what kind of molecule you have. In a polar molecule, it's the difference in electronegativity. In a polar molecule, it's like a tug of war between two atoms over the electrons. And the greater the difference in the strength of the two atoms, the more the electrons will be pulled and the larger that permanent dipole will be. So, which would have a stronger dipole then, HCl or HBr? Well, chlorine is higher in group 17 than bromine, which means chlorine has a greater electronegativity than bromine. So the difference between hydrogen and chlorine will be larger, and we would expect it to have a stronger dipole. So the answer, of course, would be the HCl. What about nonpolar molecules? In the case of nonpolar molecules, electronegativity is unimportant. In a nonpolar molecule, it's a tug of war between two equally matched opponents. If it's a hydrogen molecule, each hydrogen is equally strong. If it's a fluorine molecule, each fluorine atom is equally strong. So in nonpolar molecules, it's the number of electrons in the molecule. You may remember when we were speaking about this a few minutes ago, what makes a nonpolar molecule have its temporary dipole is the random motion of the electrons from one side of the molecule to the other. So the more electrons that are moving back and forth, the greater that temporary dipole will be. So let's compare propane and decane. Propane, with 3 carbons and 8 hydrogen atoms, has a total of 26 electrons in the molecule. C10H22 has 82 electrons in the molecule. And our rule is whichever molecule has the greater number of electrons should have the greater temporary dipole. And so decane will have stronger bonds than propane. And it's pretty obvious if you looked at the two substances, because propane is a gas at room temperature and decane is a liquid. The reason decane is a liquid is because there are stronger bonds between the molecules, holding them more tightly together. So, in summary then, for polar molecules, it's the difference in electronegativity that we care about. In nonpolar molecules, electronegativity is a non-issue. All we really care about in that case is how many electrons are in the molecule. So, which one is stronger, the permanent dipole in a polar molecule or the temporary dipole in a nonpolar molecule? The answer is, it depends. There is no one single answer for that question. So what we need to know is, what does it depend on? What is determining which of these two will be stronger? Well, for polar molecules, they are normally stronger than nonpolar molecules, and that's logical because a polar molecule has a positive and negative end all the time, and a nonpolar molecule has it only part of the time. So when I say all other things equal, if a polar and a nonpolar molecule have the same number of electrons, they would be equal in terms of their temporary dipole. So the only thing that would be different is that electronegativity difference that makes a permanent dipole. So, for example, let's compare methane and water. Each of these have 10 electrons, and so they're equal in that point. Methane, however, is a nonpolar molecule. It's a tetrahedron, but water is a bent molecule, which means it's going to have a permanent dipole. An easy way to compare the strength of their intermolecular forces is to look at their boiling points. The higher the boiling point, the stronger the bonds must be, because in order to boil a liquid, you have to break the bonds that are holding those molecules together. So methane boils at a very low temperature, minus 164 degrees Celsius. So it's very easy to boil methane because its intermolecular forces are pretty weak. Water, of course, boils at 100 degrees Celsius. That's 264 degrees higher, which tells us the bonds in water must be substantially stronger than the bonds in the methane. So in this case, polar definitely beats nonpolar. Now let's take a look at a second example, oil versus water. Oil is very much like methane. It's simply a long chain of carbon atoms with hydrogen atoms attached to it. It's also a very nonpolar substance. However, oil won't even boil. You can heat oil as hot as you want. Eventually it might catch on fire, but you can heat oil well above the boiling point of water and it will just sit there. It's not going to boil. That's why if you've ever noticed, if you put a piece of meat into a skillet with hot oil and it begins to splatter, that splattering is not the oil, it's the water boiling when it hits the hot oil. So because oil has a much higher boiling point than water, that means that oil has stronger intermolecular forces. So even though oil does not have a permanent dipole, because oil molecules have a lot of electrons, it's got a very strong temporary dipole. So temporary can beat permanent if the temporary dipole is large enough, meaning if that molecule has a lot more electrons than the molecule with the permanent dipole. One thing you will need to be able to do is to identify whether a molecule is polar or nonpolar. Now, this may seem to be a daunting task because there are millions of molecules out there, and I can give you any one of those millions on a quiz or exam and expect you to tell me whether it's polar or nonpolar. Luckily, there is a fairly easy way to do this. If you think back to our chapter on acids and bases, there are thousands of acids, and I told you that you would have to be able to identify whether an acid was strong or weak. And what made that easy is there were very few strong acids. Only 6 of them. Almost all the acids were weak, so you only had to memorize a very small list. Well, the same thing is true with polar and nonpolar molecules. Most molecules are polar, so all we have to do is just learn those few instances when a molecule will be nonpolar. So there's a few basic rules that you can follow. Our first rule, which is pretty obvious, is if there's only one element in a molecule, it has to be nonpolar. The only way a molecule becomes polar is if there's unequal sharing between the atoms in the bond, and with being the same element, they have to share equally. So things like O2, P4, S8, those are all nonpolar molecules. It doesn't really matter what the molecule looks like. 8 sulfurs, they all have to share equally. The 4 phosphorus atoms have to share equally. So that's a simple one. Now, the more complicated one is when there are 2 elements, because when there's 2 elements in a molecule, it can go either way, polar or nonpolar. So it comes down to the shape of the molecule. If you remember back to chapter 12, when you have 2 elements in a molecule, it's possible that they can be in a straight line or they can be bent. So if 2 elements are in a straight line, if it's a linear arrangement, like carbon dioxide, then that molecule will be nonpolar, because the 2 oxygens, even though they're stronger than the carbon, they are pulling against each other and they're canceling each other out. So carbon dioxide is a nonpolar molecule. And not surprisingly, carbon dioxide is also a gas. Gases, by their nature, have weaker attractions. Rule number 3 is if you have 2 elements in a trigonal planar arrangement. So a trigonal planar molecule would be something like sulfur trioxide. In the case of sulfur trioxide, the 3 oxygens, even though they're stronger than the sulfur, they are essentially pulling against each other and they're canceling one another out. So if you have 2 elements and it's a trigonal planar arrangement, it will also be nonpolar. And again, not surprisingly, sulfur trioxide is a gas. Our next rule is if you have 2 elements in a tetrahedral arrangement. So something like carbon tetrafluoride. The 4 fluorines in this tetrahedron are much stronger than the carbon, but they are equally spaced around the center, which means the 4 fluorines are fighting against one another and they are canceling one another out. So this molecule is also nonpolar. It also happens to be a gas. So let's summarize briefly the material we just finished covering. First of all, if there's only one element in a molecule, then that molecule will always be nonpolar. So those are the easy ones. Similarly straightforward, if there are 3 or more elements in a molecule, it will always be polar. So really the only ones that we have to give a lot of thought to are molecules that contain exactly 2 different types of elements. If there are 2 elements in a molecule, it can go either way. It might be polar, it might be nonpolar. As we saw a few minutes ago, it depends on the shape of the molecule. So to have 2 elements in a molecule and for it to be nonpolar, all of the atoms have to be in balance with each other, which means the molecule has to be very symmetrical. So for 2 elements, that occurs in 3 cases, as we just saw, if the molecule is linear, or trigonal planar, or tetrahedral. Those are the 3 very symmetrical geometries of the molecules. In those cases, the molecules will be nonpolar. Otherwise, the molecules will be polar. Now, hydrogen bonding is a special type of permanent dipole. we separate it from your regular permanent dipoles because it's much stronger. Hydrogen bonding is simply a very powerful permanent dipole, and as you can probably guess, it contains hydrogen, but not just hydrogen. There's essentially three instances where we commonly find hydrogen bonding. The first one is if hydrogen is bonded to fluorine. Fluorine is a very electronegative element, the most electronegative element. So the electrons are pulled very strongly to the fluorine, producing a very powerful permanent dipole. So the hydrogen becomes positive, the fluorine into the molecule becomes negative. This also happens when hydrogen is bonded to nitrogen, also a fairly electronegative element. So for example, in something like ammonia, the nitrogen is pulling the electrons from the three hydrogens, the ammonia or the nitrogen end of the molecule becomes negative, the hydrogen end becomes positive. And then our third case is if hydrogen is bonded to oxygen. So something like a water molecule, oxygen of course is much more electronegative than hydrogen, so electrons are pulled toward the oxygen and away from the hydrogen, and that makes the oxygen end of the molecule negative and the hydrogen end of the molecule positive. So what should we know in the end about intermolecular forces? First of all, intermolecular forces are produced by the unequal distribution of electrons. Whenever the electrons are pulled to one side of the molecule or the other, we get intermolecular forces, and that happens in both polar and nonpolar molecules. Nonpolar molecules share electrons equally. So they're normally nonpolar, but they can temporarily become polar. As the electrons move around, they can move to one side, form these temporary dipoles. And the forces of attraction in nonpolar molecules are commonly referred to as London forces. In a polar molecule, the electrons are always shared unequally because the atoms have different electronegativities. So these molecules have a permanent dipole, and as we said earlier, their forces of attraction are known as dipole forces, or sometimes they're referred to as dipole-dipole forces. The strength of a temporary dipole depends on how many electrons are in the molecule. So if molecules are nonpolar, the more electrons in the molecule, the stronger its intermolecular forces will be. For permanent dipole, for polar molecules, it's all about the electronegativity. The greater the difference in electronegativities of the elements, the more powerful that permanent dipole will be. And then we just talked about hydrogen bonding. Hydrogen bonding is a permanent dipole. It's just a very powerful permanent dipole, and it's observed whenever a molecule contains a fluorine bonded to a hydrogen or an oxygen, or a hydrogen to an oxygen, or a hydrogen to a nitrogen. And the whole molecule doesn't have to be hydrogen and nitrogen, for example, as long as an H bonded to an N is part of the molecule, or an H bonded to an O is part of the molecule. So let's wrap things up by working through a few practice problems. In these problems, what I want you to be able to do is to look at a molecule and determine whether the forces of attraction are temporary dipole, meaning it's a nonpolar molecule, permanent dipole, or hydrogen bonding. Both of those would occur in a polar molecule. So for our first example, let's take a look at formaldehyde. Now if we apply our rules, the first thing we'll notice is there are three elements in this molecule, which means it's automatically a polar molecule. So the question is it just a permanent dipole, or is it hydrogen bonding? Hydrogen bonding is a possibility because hydrogen and oxygen are both in this formula. The key thing is, are the two atoms bonded together? To figure that out, we need to sketch out the molecule. If we sketch out formaldehyde, we'll see that it is a nice trigonal planar molecule, but the hydrogen atoms are not bonded directly to the oxygen. The H's are bonded to the C instead. So if the H isn't directly bonded to O, it can't be hydrogen bonding. It's got to be permanent dipole. For our second example, let's look at phosphine, pH 3. Now, phosphine has only 2 elements, which means in this case it's all going to depend on the shape of the molecule. With 2 elements, it depends on the geometry. So once again, we'll need to sketch it out. If we do, you'll notice that pH 3 is a trigonal pyramid. It's not trigonal planar because the phosphorus has a non-bonding pair of electrons. So this molecule is not symmetrical, which means it must be polar and thus has a permanent dipole. Octasulfur, again, if there's only 1 element, that makes it relatively simple because the rule was if there's only 1 element, it is going to be a non-polar molecule, which means it will have a temporary dipole. We don't really need to know what the shape of the molecule is if there's only 1 element, but sulfur is a rather interesting molecule. It's an octagon, sort of like a bent-up stop sign. And finally, difluoromethane. Now, difluoromethane has 3 elements, so we know it's going to be polar. The question is it hydrogen bonding or just regular permanent dipole? Once again, hydrogen bonding is a possibility because we have both hydrogen and fluorine. We need to sketch the molecule out to see whether the hydrogen and fluorine are attached to each other. If we do that, we see that the hydrogens and fluorines are not actually bonded to one another. All 4 of those atoms are bonded to the carbon. So it's not hydrogen bonding, it's just going to be a permanent dipole. In our previous video, we talked about intermolecular forces, and I mentioned that those forces determine the various properties of liquids. So in this video, we're going to look at the different properties liquids have and how those are related to intermolecular forces. So there's 5 basic properties of liquids we're interested in. The boiling point, the temperature at which the liquid boils, viscosity, surface tension, vapor pressure, and the heat of vaporization. So each of these, as I mentioned before, depends on the strength of the intermolecular forces, and each of them is either going to be directly related or inversely related to those intermolecular forces. If they're directly related, that means that the stronger the intermolecular forces, the greater that particular property will be, and if they're inversely proportional, then it will be the opposite. The stronger the forces, the less that property will be. So let's start out and take a look at boiling point. The boiling point is essentially the temperature at which a liquid boils. We can see that in this boiling water, it's at 100 degrees Celsius or about 212 Fahrenheit. And so how is the boiling temperature of the liquid related to these intermolecular forces? Well, if you think about it, in order for a liquid to boil, we have to break the bonds between those molecules. So logically, the stronger the bonds between the molecules, the more energy we would imagine that it would take to break those bonds, and therefore we'd expect stronger bonds or stronger intermolecular forces to give us a higher boiling point. So the boiling point is directly proportional to the strength of the intermolecular forces. If I asked you to name a viscous liquid, you would probably come up with something like honey, or perhaps motor oil. Both of these are viscous liquids. Something that's viscous basically means that it flows slowly. Sometimes people say the liquid is thick. But viscosity is more technically a resistance to flow. So the more viscous or the higher the viscosity of a liquid, the slower it flows. Now, if we think about this on a molecular level, it makes sense. When this honey is flowing out of a container or off of this wooden spoon, the molecules in the honey are flowing past one another. and as they flow by one another, they have a tendency to stick together because there are intermolecular forces. Logically, the stronger those intermolecular forces, the more difficult it will be for those molecules to slide by one another, and the slower they are going to move. So based on that, we would assume that viscosity, like the boiling point, is directly proportional to intermolecular forces. The stronger the bonds between the molecules, the more difficult it is for them to flow past one another, and the more viscous the liquid will be. The scientific definition of surface tension is a little complicated, so I think it might be easier if we just look at some examples of surface tension in action. This is a water strider or a water bug, and you've probably seen them flitting around on the surface of water. These insects are actually denser than water, so by all rights they ought to sink, but they don't. You can see that their legs are making an indentation in the water. It's almost like the water's got a film of plastic over it, and the insect is pushing down and making a dent or an indentation in that surface, but it's not breaking through. And the reason it doesn't break through is intermolecular forces. There are attractions between the water molecules, and for the insect to break through, it has to break those bonds, and the weight of the insect simply isn't strong enough to do that. You've also certainly seen water bead up on the surface of a car. The reason the water beads up is due to surface tension. And we'll talk in a little bit about exactly why the water beads up. So, surface tension, like viscosity and boiling point, is directly proportional to the strength of these intermolecular forces. If the bonds in this liquid were weaker, it would be easier for the insect to break through, and it would sink. Water just happens to have very strong attractive forces because, as we learned earlier, water has hydrogen bonding. So back to our question we asked a moment ago, and that is, why does water bead up on a waxed surface? Is it because the water doesn't like wax? Or does wax repel water? And the answer is no. There's actually no such thing as repulsion when it comes to molecules. All molecules attract each other. So why is the water appearing to try to get away from the wax? Because the wax is actually attracted to the water. The key thing is how much is each thing attracted to the other. Water does like wax. There is an attraction between these water molecules and the molecules of the wax, but water loves water. Water would much rather bond with other water molecules than it would with the wax. Why does it want to do that? It's very simple. To get stronger bonds. We've talked about that earlier in the semester, and the fact that most physical and chemical changes, what drives them, what makes them happen, is that desire to get stronger bonds. Chemical compounds form because the atoms want to get stronger bonds. So the water molecules are beating up because in the droplet, all those molecules floating around inside the drop are surrounded by other water molecules. If the water spreads out on the surface, then the molecules find themselves bonding to the wax, and that's simply less satisfying. The molecules never want to give up stronger bonds to get weaker bonds in return. So, what's wrong with this picture? This is a bottle of Rain-X water repellent. Well, the problem is, as I mentioned a moment ago, molecules don't repel each other. There's no such thing as water repellent. I've always said if there were truth in advertising, these would be called water-less attractants, because that's really what they are. The chemical in here, usually a silicone, a nonpolar material, simply makes a surface less attractive to water, and therefore the water prefers the company of other water molecules. When you spray a water repellent on a fabric, you notice, oh, the water droplets bead up, and the reason is very simple. They would rather bond with each other and get stronger bonds then get the weaker bonds they would get with that water repellent, so to speak, silicone coating. Our next property is called vapor pressure. If we take a look at this diagram, at the beginning we have a container of liquid inside a sealed jar. Now the molecules of the liquid, like all liquids, will begin to evaporate. Molecules will escape from the surface of the liquid and they will move up into the air. As more and more of the molecules enter the air, some of the molecules begin to randomly bounce around and they will go back into the liquid. So in the beginning, it's a one-way trip. All the molecules are leaving the liquid. They are evaporating or vaporizing. After a time, some of the molecules begin to condense, so condensation occurs, but still vaporization is happening faster than condensation, so more and more molecules begin to build up in the air. Eventually, we get to a point where there's so many molecules of the liquid vapor in the air that they're now condensing just as fast as they're vaporizing. So we get to a point where for every molecule that leaves, another molecule returns to the liquid, and we've reached a state which is known as dynamic equilibrium. Equilibrium means balance, and so we have a balance between vaporization and condensation. The word dynamic simply means things are changing. So dynamic equilibrium basically means that there's two changes occurring, but they're happening in opposite directions at equal rates. So as you get more and more molecules of the vapor up here, it causes an increase in the pressure. There's more molecules now bouncing around inside the container, hitting the surface of that glass, and that extra pressure caused by the vapor is called the vapor pressure. So how are vapor pressure and intermolecular forces related? Well, let's think about it. If the bonds are strong in the liquid, it's going to be difficult for those molecules to escape, and so you're going to get less vapor molecules. If the bonds in the liquid are weak, they're going to escape very rapidly, and you're going to get lots of vapor molecules, and thus more pressure. So unlike the previous properties, vapor pressure and intermolecular forces are inversely proportional. The stronger the bonds in the liquid, the less vaporization you get, and the less vapor pressure you get. The last of our properties is called heat of vaporization. It's basically the energy involved in vaporizing a liquid. Do you suppose it requires energy to vaporize a liquid? Obviously it should, because when you vaporize something, you're essentially breaking bonds. And as we've said many times, breaking bonds always requires energy. So the heat of vaporization is simply the amount of energy that's required to change a liquid into a gas. Now, it doesn't necessarily have to be at the boiling point. This slide's not entirely correct because vaporization can occur in a liquid at any temperature. Water vaporizes at room temperature when it evaporates. But in general, it's simply the amount of energy you need to convert the liquid into a gas. So, how do we suppose these two would be related? If you think about it, if the bonds in the liquid are stronger, it should take more energy to break those bonds. So we would anticipate that, like our first three properties, it's going to be directly proportional. So of the 5 properties that we studied, only the vapor pressure was inversely proportional to the intermolecular forces. The other 4 were all directly proportional. Now there's also another property that's similar to this called the heat of fusion, and fusion simply means melting. So the heat of fusion is the amount of energy required to change a liquid from a substance from a solid to a liquid. So which of these do you suppose is greater? Does it take more energy to vaporize a substance or to melt a substance? Well, for water, the heat of vaporization is 2,260 joules per gram. That's a lot of energy. So every gram of water that turns from a liquid to a gas requires 2,260 joules. So, do you suppose the heat of fusion will be higher or lower than that? Well, let's think about what's happening. When you vaporize a liquid, you're actually breaking bonds. When you melt a liquid or melt a solid, all you're doing is loosening or weakening the bond. So the question becomes very simple. What requires more energy, breaking bonds or loosening bonds? And logically, we would expect that breaking the bonds in vaporization ought to be greater, and it is. The heat of fusion for water is substantially less, about 1/7 as much. Only 335 joules are required to melt a gram of ice. 2,260 joules are needed to vaporize a gram of water. And this is true for all substances. No matter what the material is, the heat of vaporization is always going to be significantly greater than the heat of fusion. We can combine what we learned in Chapter 14 with what we talked about back in Chapter 7 when we first began to discuss energy and physical and chemical changes. This particular diagram is called a heating-cooling curve, and it shows what happens to a substance as you add energy to it or as you remove energy. So the amount of energy is increasing along this axis and the temperature is increasing on this axis. So let's suppose we started out with a solid below its melting or freezing point. This could be water, say at -20 degrees Celsius. What happens if you take an ice cube out of the freezer? And that ice cube, they're usually at about -20 degrees Celsius. The moment you begin to warm up that ice cube, what happens? Now, most people will say, oh, the ice cube begins to melt. But that is not the case. The ice cube will not melt. Ice doesn't melt till you get to its melting point of 0 degrees Celsius. So when you pull that ice cube out of the freezer, the next time you do it, feel that ice cube, and you'll notice it's not wet. It's not melting. It feels dry and rough. That ice cube will not melt until its temperature reaches the melting point. So the first thing that's going to happen is the temperature of the ice is going to rise. Once it reaches the melting point, then it will begin to melt. It'll change from a solid to a liquid. So you can see below the freezing point, it's all solid. Once we get to the melting point, now the solid slowly begins to convert to liquid. Now what happens if you take that piece of ice once it's reached 0 degrees and you hit it with a blowtorch? You put a flame on that ice cube. Can you raise the temperature of that ice cube? The answer is no. You can heat the heck out of that ice cube, but it is not going to go above 0. It's going to follow this flat plateau here. The more energy you put in, the faster it's going to melt. But every 335 joules of energy you put into that ice cube is going to melt 1 more gram of ice until it's completely melted. Once it is completely melted, now that it's all liquid, if you continue adding energy to it, the liquid molecules will simply move faster and the temperature will rise until it reaches the boiling point. Once the liquid reaches the boiling point, it's going to slowly turn from a liquid to a gas. Now you can heat that liquid all you want. If you're boiling water on your stove and you think you can cook food faster by simply turning the burner on high and that water's just boiling like mad, if you put a thermometer in there, it's going to be 100 degrees. Whether it's a gentle simmering boil or a rolling boil, you can't heat it above 100 degrees Celsius, at least not with doing something special. So your food's not going to cook any faster if you boil it rapidly or you boil it gently, because the time required to cook food depends on the temperature you cook it at. And when you cook something in boiling water, it's always cooking at 100 degrees. Now, once the water is completely vaporized, if you continue adding energy, you can heat the water vapor up basically as hot as you want until you get to maybe 2,000 to 2,500 degrees Celsius. And then the energy is so great, the water molecules themselves will actually break apart into hydrogen and oxygen. Now, you take a look at this other little figure. It sort of summarizes this. So melting and freezing are basically the same process, just in reverse. So if you look on the curve here, if you go from left to right, you're melting a solid. If you go from right to left, you're freezing a liquid. Same thing is true above. We have evaporation or vaporization and condensation. So if you're moving from left to right, you are vaporizing or evaporating the liquid. Right to left, you're condensing it back into liquid water, or whatever the liquid happens to be. Now, it is possible in some cases to go directly from solid all the way to gas. That particular process is called sublimation. If you've ever kept ice cubes in your freezer, sometimes you dig down in the ice tray and you find these little tiny misformed ice cubes. You know, how did I get those tiny little oddly shaped ice cubes? What's been happening is those ice cubes have been in the freezer a long time, and molecules of water have simply been breaking free directly from the surface of the ice and becoming vapor, and so the ice has essentially been vaporizing. And the opposite process is possible as well. That's what frost is. When you see frost on a cold day or after a cold night, that frost is simply vapors of water turning directly into crystals of ice. Vaporization is a general term that simply means a liquid is becoming a gas. But there's actually a couple of different ways that can happen. One way is by evaporation, and the other is boiling. So each of those has a couple of characteristics that identify it. For example, evaporation occurs over a wide range of temperatures. So a liquid can evaporate at any temperature in which it's liquid. So ice water at 0 degrees Celsius will evaporate. Boiling water will evaporate. It'll simply evaporate faster. Boiling, on the other hand, occurs at a specific temperature. For water, we say that the boiling point of water is 100 degrees Celsius. It doesn't boil at 95 or 105, it boils at 100. With evaporation, it occurs only at the surface of a liquid. So for a liquid to evaporate, molecules have to break free from the surface and escape into the air. On the other hand, boiling can occur anywhere in the liquid. So it depends on where the heat is. In a pan on your stovetop, you normally see the bubbles forming at the bottom of the pan. If you boil water in a microwave, those bubbles can form anywhere. So is the boiling point of water always 100 degrees Celsius? Well, it seems like I just said that, but like many things, they're not always as simple as they appear at the beginning. Let's take a look and see what exactly has to occur for boiling to happen. Essentially, for boiling to take place, the vapor escaping from the liquid has to be able to push the air out of the container. So the air is pushing down on the surface of the liquid with 1 atmosphere or 760 torr or whatever units you use of pressure. So the vapor of the liquid has to push up with the same amount of force. That's what we learned about earlier, called the vapor pressure. And we also learned, of course, that vapor pressure is not going to be the same at every temperature, because for molecules to escape from a liquid, they need energy. Every gram of water molecules that escape from that liquid need 2,260 joules of energy. So logically, the more energy you put in, the faster that's going to happen. So the fact is, water will not always boil at 100 degrees Celsius because atmospheric pressure is not always the same. At sea level in Stockton, the atmospheric pressure is about 1 atmosphere. At different elevations, that pressure will be different. But the overall rule is very simple. When the vapor pressure of the liquid pushing up equals the atmospheric pressure pushing down, then the liquid will boil. So if you change the atmospheric pressure, you'll change the amount of vapor pressure required to boil, and that will change the boiling point. 100 degrees Celsius we usually refer to as the normal boiling point of water. That means its boiling point at 1 atmosphere of pressure. So this graph shows the vapor pressure of water at various temperatures. And interestingly enough, you'll notice that the vapor pressure of water reaches 760 millimeters of mercury, which is 1 atmosphere, at precisely 100 degrees Celsius. That's why water normally boils at 100 degrees Celsius, because that's the temperature at which the vapor pressure of the water is equal to that atmospheric pressure pushing down on it. Now, what if we went up to Lake Tahoe? If you get up to Lake Tahoe, the atmospheric pressure is going to be less. It's only going to be about 80% of what it is in Stockton, which means it's going to take less energy to boil the water. If we look at the graph, when we get up to about 93 degrees Celsius, we reach a vapor pressure of 600 millimeters of mercury, and that's about what the pressure is in Tahoe. So water in Lake Tahoe will boil at about 93 degrees Celsius. If we reduce the pressure even further, if we were to put the water in a vacuum container and pump a lot of the air out, if we got the pressure inside our container all the way down to 25 millimeters of mercury, that water would boil at room temperature. You could hold it in your hand and it would feel completely cool. So boiling does not always mean hot. I often ask students to tell me, what's the first word that comes into your mind when I say boiling? And they normally say hot. But boiling is not a particular temperature. Boiling is a change of state. It can happen at a high temperature. It can happen at a low temperature. One thing I always find interesting in teaching chemistry is at the beginning of the semester, most students have very little knowledge about science, and so I can't get into very detailed explanations, but I always tell everybody, the farther we get on into the semester, the deeper your understanding is going to be, and there's a lot of questions that we'll be able to answer in more depth, and you'll be able to understand perhaps some everyday things you've observed and never really knew why they were the way they were. So here's a few questions to think about. I always love to ask my students this one. How long does it take to cook a 3-minute egg in Lake Tahoe? Now you're probably thinking, hey, wait a minute, is that a trick question? It's probably 3 minutes. Well, I suppose it could be, but a 3-minute egg is a soft-boiled egg. So when I say a 3-minute egg, I mean an egg that has been cooked to the consistency that you would normally expect a 3-minute or soft-boiled egg to have. So we're going to make this a multiple choice question. Your possible answers are 3 minutes, less than 3 minutes, or more than 3 minutes. So take a moment and think about that. You can pause the video if you wish, and then we'll look at the answer. And the answer, of course, is more than 3 minutes. And the reason is very simple. I mentioned a little while ago that the time required to cook food depends on the temperature at which you cook it. That's why in boiling water, whether it's a gentle boil or a vigorous boil, it's still 100 degrees Celsius. It still takes the same amount of time. But in Lake Tahoe, as we just found out, water boils at only 93 degrees. So we're cooking our egg at a lower temperature, and that means it's going to take longer to get that done. I'm sure all of you are familiar that when you cook food in your oven, the higher you turn the temperature in the oven, the faster the particular food is done. All right, here's another one that you've probably noticed. You get out of a swimming pool on a hot summer day in Stockton, yet you feel a chill. You're cold. And well, how in the world can we feel cold when we get out of a pool on a 95-degree day? And the answer is, it has to do with heat of vaporization. When you get out of that pool, you're wet, and the water on your skin begins to evaporate. And of course, as we learned a little while ago, every gram of water that evaporates from your skin needs 2,260 joules of energy. And where do you suppose it's getting all of that energy from? That's right, it's getting it from you. It's taking that energy out of your body,
and that's what's making you feel colder. That's why they often put wet cloths on people when they have a fever. They'll put it on their forehead, and that evaporating water will help cool the person down. Now, a lot of people in Stockton have swamp coolers. I've seen a lot of people with those on their roofs. Maybe some of you have those. A swamp cooler is sort of like an air conditioner, only it's much simpler. All it really is a belt that goes around through a tub of water, and the water evaporates off of the belt, and of course as the water evaporates, it takes energy from the belt and the belt gets colder. So why don't swamp coolers work in swamps? They only use them in dry climates. And the answer is very simple. It goes back to our old buddy, dynamic equilibrium. Dynamic equilibrium, again, means that processes can happen in two directions. If you're in Louisiana in the summertime and it is incredibly humid, maybe the humidity is 100%. At 100% humidity, the air is saturated with water molecules. So every time a water molecule evaporates from your skin or from the swamp cooler, another water molecule condenses. So a gram of water molecules leave, and they take with it 2,260 joules of energy, yay, but then another gram of water molecules from the air, they condense back down and they release 2,260 joules of energy, so you have ended up gaining nothing. So swamp coolers really only work in dry climates. In Arizona, very common. Almost everyone has a swamp cooler because it's a hot, dry climate. And finally, one last question. Why does food cook faster in a pressure cooker? Well, the whole key behind a pressure cooker is pressure. I mean, inside a pressure cooker, it's sealed so that when the water begins to boil, all of that water vapor increases the pressure inside of the pressure cooker. And as we learned a little bit ago, the boiling point of water depends on the external pressure it's pushing against. Inside that pressure cooker, instead of the usual 760 millimeters of mercury, the pressure might be 1,200. At that higher pressure, it's harder for the water to boil, so perhaps you have to heat it up to, say, 120 degrees Celsius. And at 120 degrees Celsius, now the water will boil again, but your food is cooking at a much higher temperature. Rule of thumb for cooking, or for chemical reactions in general, is every 10 degrees Celsius that you increase the temperature, it cuts in half the time needed to cook the food. So pressure cookers are very convenient for cooking foods much faster.
Well, that wraps up our discussion of liquids. At this point, you should be able to identify the various types of intermolecular forces, whether they're temporary dipole, permanent dipole, or hydrogen bonding. You should be able to tell how the shape of a molecule can affect those properties as well, along with understanding the various physical changes of state we talked about and the energies involved in those changes of state. We're now going to move on into Chapter 15. That's the final chapter of the course, where we're going to talk about solutions. So let's go ahead and get started.